All right, here we are in Unit 6. This is Lesson 2. We're talking about uh, how humans influence climate change. There's a poor little seal sitting there on its little floating island. All right, so in this lesson, we're talking about Shishmaref, however you say that, which is actually it is in Alaska. So there is permafrost all over the world. That's why I was hesitating because I forgot where it was. But permafrost is really common up in any of like Greenland, like Norway, Alaska, Canada, all the very up north places, Russia, things like that. Okay, and so what it is it's basically loose soil and sand that's frozen. So here we have a picture of a building that's 400 years old, and it looks like it's just falling into the ocean. And then here we have a picture of permafrost, and this permafrost has melted. So the ice that's holding all the soil together has melted, and it means that the soil can be eroded away, or it could be like washed away very easily, just because there's nothing holding it together anymore. So it says the amount of sea ice and permafrost has steadily decreased over the last century. How has the loss of ice allowed waves to erode the land and destroy the property? What might be causing this melting? So what I said was that what could be causing the melting is maybe it's warmer all the time, or during the warm months like summer, maybe it is hotter, so more ice melts. Or it could be that during the winter it doesn't get as cold, so the ice hasn't been, anything that melts doesn't refreeze. And it could also be that maybe the sea ocean is warmer, so as it comes along, the permafrost, as the permafrost and the kind of the waves meet, the waves melt the permafrost faster. Or it could be all of them. Okay, so exploration 1 is about climate. Climate is a description of weather long term. So it says, you can actually see that right here. Weather describes the conditions of the atmosphere over a short period, like a hot sunny afternoon or whatever, the weather is that day. While climate describes weather conditions over a long period, like 30 years. Even usually 1, 2, 3, 4, 5, that's not really describing climate so much. It's usually decades, centuries is what climate is over a really long period of time. And it says our current global climate is the average. So we're going to use surface temperature and global climate a lot. And right here it tells us that global climate is the Earth's average surface temperature, and currently it is about 61 degrees. They do that by, essentially they have thermometers all over the Earth and throughout the oceans on the surface, and they add up all the temperatures, and that's how they get this average of 61 degrees. Okay, so 2 says, why do you think the temperature range on Earth is so different from the temperature range on the moon? And so we have this picture right here, and it says that, they're both basically the same distance away from the sun. So this is very deceiving. Obviously, the Earth and the sun are not, like, this is not to scale. If you were, if you had the sun, and the sun was a tennis ball and you were holding it, the Earth is about, I think it's about like a room or a couple rooms away from you. It's pretty far. So this is squished together. But the point is that the moon and the Earth are the same distance. So the moon is from negative 178 degrees Celsius to 117 degrees Celsius. It says that right here. That's the moon. And whereas the Earth is negative 88 to 58. So the moon gets much colder, and it also gets much warmer. What's up with that? make a list of ideas. So some of my ideas were that the moon doesn't, so the Earth spins around every 24 hours, right? It's spinning around. The moon doesn't actually spin around, rotate. It relative to us, that's why it always looks the same to us, because the same side of the moon is always, like, the same exact part of the moon is always facing Earth. It's the worst arrow ever. So it kind of rotates relative to the sun, but every month, because it's spinning around like this. So, you know, the moon would be over here, one side would be lit, and then it'd have to spin all the way around, right? And this side would always be facing. So when it was over here, it would be like this, right? I'm shading one side. Right, so when it's on the other side of Earth, you know, or even over here, right, it'd be like that. The opposite side is facing the sun. So all sides of the moon do actually see the sun. They just don't see us. But I said it's because it has to do with that, but also because there's no atmosphere. So going down. The climate system. So this talks about the greenhouse effect. And so you actually learn a lot more about this later next year and stuff, but the greenhouse effect is essentially you've got the sunlight, and so sunlight will enter the atmosphere, and some of the sunlight is reflected by particles in the atmosphere, moisture in the atmosphere, water in the atmosphere, things like that. And some of it gets reflected by the surface. So, you know, the water will reflect some light. The mountains will reflect some light. Everything's reflecting some sunlight, but a lot of that sunlight gets to the surface, right, as energy. And so once it reaches the surface, right, a lot of it reflects back up into space. And why does this say infrared radiation? Well, what happens is the energy waves that are coming into Earth are of a certain wavelength, and then they will reflect off of things, and those things will absorb some of that energy. But a lot of that energy is still reflected, right? I mean, this is why you can see things. Like bright things reflect lots of colors, like, you know, white reflects lots of light, and darker colors like black absorb a lot of light. But you can still see black paper. Why is that? It's because it's still reflecting some energy. A lot of that energy is infrared radiation, and that energy can be absorbed by molecules that are floating up in the atmosphere. So because the atmosphere is filled with, you know, tiny atoms and molecules, the energy that's passing through those molecules will move them around more, and it will cause them to absorb some energy, heat up, move faster. And the more, basically, and certain particles do that more than others. So like we talk about CO2 a lot because CO2 actually absorbs lots of the energy. Methane absorbs lots of energy. And when you have more of those gases in the atmosphere essentially can hold in more energy. Okay, so then you have this lab. The lab is, you can skip this lab. Okay, so then you have this part. This is the temperature ranges on the Earth and Moon. So, unlike the Earth, the Moon has no atmosphere. Explain why the range of temperatures on Earth is so different than on the Moon. Cite evidence. And so, basically, what I did here was I just said how there's no atmosphere, and you could actually. This is a good lab to kind of do on your own. You can do this on your own, and you might see this for real. But the whole greenhouse effect can't take place on the moon because there's no atmosphere. So there's no atmosphere to capture any of that reflected light. So, when you're on the dark side of the moon, you're just basically an empty space. There's nothing to keep any warmth there. Or even when you're on the sunny side of the moon, there's nothing to hold that warmth in. So, but it's facing the sun, so it gets way hotter. But on the Earth, because we have the atmosphere kind of acts like a blanket and absorbs the energy and distributes it around. Hi, Bradley. So, Exploration 2. Exploration 2 is about global climate change. So this says that, 100 million year old fossils of tropical ferns have been found in Antarctica. So they actually have found, and again, you go into this a lot in the future. I know as a 7th grade teacher, but there were like these big, like fern plants that are just these giant plants, ferns, and they look just like a ferns that you'd see here if you went up into like Tahoe or Yosemite and were like deep in the forest, and it was like fall and you have these big leaves. And where did those come from if it's Antarctica? And so they have found these in Antarctica, which shows that Antarctica's climate at one point was warm and rainy. And obviously now it's not warm and it's not rainy, it's cold and it's dry. A lot of times people don't think of dry because it's snow, but snow and winter air is very dry. That's why in the winter, a lot of times, people have like your skin is a little bit more dry a lot of times during winter. Your lips get chapped and stuff like that. So we have lots of ways that we look for climate data. Some of it is in rock formations. Other things are in like tree rings. We look at how fossils are distributed around the Earth. And we also look at, you can also look at gas that's trapped inside of ice that's formed. So when ice, every year, when it snows, right, think you have a surface. Like if you're in a place like Antarctica, you've got your surface, and this is all ice down here. This is ice. And as it snows, right, every year, it'll snow. Here's my snow. And you'll get like a light dusting of, there'll be new snow on the top of the surface, right? And then the next year, there's more snow. So there's more snow on top. And as more layers, of snow basically pack up over the years, right, it packs itself into ice. But what's trapped within all of the snow is the air, and that air can't escape once it's compressed down and becomes ice. So you can drill down into the ice and measure what the air was like over different times. So here's a map that actually shows that. This is using ice cores over the last 800,000 years. So they've dug way down into the ice, and they can tell what a year is because it has to do with things like there'll be like volcanic eruptions or certain major things and they'll see things, like you might have a core of ice. So here's my ice core, which is straighter than that, but here's my ice core. And, maybe it's like dirty right here, and it has the same type of everything that is when this volcano erupted. So, this is when the volcano erupted, and then another time maybe that happened, or maybe there was like a flood, and so it distributed some things at one point in time. And you can use different things like that. Also, there's more minor lines between when it, because of the annual, like the summers and the winters, it creates like some type of band action. And that's how these people who know what they're doing can actually figure out how far back in time it was. But you can see how this is the difference of average temperature over the last 1,000 years. So this is, I think that's supposed to say 100,000 years. Not sure why that says. over the last. So this is an average. So this is an average difference in average temperature over the last 1,000 years. So every mark on here is basically the average temperature difference over 1,000 years. So there's 800,000, right? So basically there's 800 points along here that make these lines. Okay, and you can see how down here is 0. So this is 0 degrees temperature difference, and so you can see how a lot of times it's a little bit less. There are years where that gets warmer. So this graph has shown that the average surface temperature in Antarctica has changed. So this, right, it's down here most of the time in the negatives because we're talking about Antarctica. So Antarctica's temperatures are going to be colder than the global average. But it has changed, right? It's gone up and it's gone down quite a bit over long periods of time, right? I think this is 100,000 years right here. This jump right here. So maybe over 75,000 years, the temperature is decreasing, and then for 10,000 years, it increased and then it decreased. So these are over really long periods of time. So if so, Earth's average temperature is currently experiencing a warming trend. Do you see how this is the present? This line over here is the present. So we're somewhere over up here. It's kind of hard to tell, but that's definitely warmer than it typically is. So this talks about causes of global climate change. So there is a number of different things. The first thing that contributes to climate change is astronomical changes. So there are things like Earth's tilt, right? Earth is not perfectly, when you think about the North and the South Pole of Earth, they're not straight up and down. They're actually on like a tilt, right? If it was straight up and down, it'd be like this. But Earth is actually tilted. So, and it's wobbling a little bit. It's like a top that's wobbling on its axis. So that changes from about 22 to 25 degrees every 41,000 years. It's wobbling slowly. And then, and so it talks about how over 26,000 years, the wobble changes the timing of seasons relative to the distance from the sun. Another thing is that we aren't, you know, if the sun is right here, we're not a perfect, obviously I'm not about to draw a perfect circle, but we're, you know, we're like an ovalish shape. So exaggerated, but, you know, if this is the sun, kind of like an ovalish shape orbit around it. So sometimes, depending on how that's wobbling that takes place, also the sun has 11-year cycles of sunspots, and they have found that when there's more sunspots, the surface is hotter, and so there are changes in the sun. Okay, those are some things that kind of like space-related things that have to do with our climate. We also have changes on our surface. So changes on our surface is the second thing that affects major thing that affects climate change, is how the Earth's surface is changing. So just in the last 50 years, or this was 66 years apart, these photos, and you can see down here, right, there used to be this glacier going all the way, filling this basically, and that is all ice, and that's all melted. So as the dark soil melts, then it's saying right here, this question. So really what this is talking about is over time, as this ice melted, then it really revealed all the dirt underneath it. Sorry, give me a second. So so as this darker area underneath it is exposed more, then the light isn't reflecting off the surface as much. So here, right, light is reflecting off the snow a lot, right? Most of the light is reflecting off of all this white snow and ice. A lot of the energy is getting absorbed by the dark area, right? So over all this period of time, a lot of this land that was once reflecting light, because this is all gone, now there's now darker light, and that will absorb more energy. Well, if the same amount of land is absorbing more energy, then it's going to just make the warming happen faster. So this is usually called they call this a positive feedback loop, because what's happening is just going to make it happen more, and it's going to make what's happening take place more and even at a faster rate. Okay, so then the third, there's also changes in ocean circulation is also related to things, changes on the Earth's surface. So in general, right, the water will, and it's kind of hard to tell from this diagram because it's 3D, but in general, you can see it really well over here. The warmer water that's on the surface will move towards the poles of the globe. And as they get towards the poles, the water will get colder and it will sink down deeper into the ocean, and then it will kind of make its way back to, typically, it like flows this direction. But see here, it ends up coming back up to the surface, and so typically, as the water gets closer to the poles, it's colder and it sinks. And then when it's near the equator, see, like over here, it's rising as well. When it's near the equator, it will warm and rise. And so changes in how the surface temperature and the water's moving around will also make certain areas change. So like in 7, it says, the movement of ocean transfers thermal energy around the globe. How might an increase of global average temperatures affect the thermal energy by the surface and the deep currents? Well, if the water is getting warmer, then all of the water is getting warmer. So what you have is you have even warmer currents headed towards the poles, which means that you have warmer water coming to the poles than you normally would. So it's going to melt stuff faster, right? And then as it melts things, it's going to sink down, but that water still won't be quite as cold as it may have. And so one of the things lots of scientists are worried about are that these patterns that we see will just completely change over time. And if these ocean current patterns completely change, that goes back to things that we talked about in the past about how, we have really common weather patterns, and a lot of that has to do with the surface temperature of the ocean. But if the ocean currents change, all that stuff could totally change, and so that could change the weather that's occurring on land pretty greatly. And so we have one of the example is the El Nino and the La Nina of that. And I'm not going to go a ton into reading this because you did that, but essentially the El Nino and La Nina is the pattern of wind that's occurring in the Pacific Ocean, and that affects us greatly because we are so close to it. So the El Nino is, it says that, so El Nino for us is like weaker winds, warmer temperatures, wetter weather, and La Nina events is the opposite, so cool, dry weather. So a lot of times you'll hear every few years they'll be talking about, is this going to be like the El Nino year? And that means that it's going to be really rainy or more rainy than usual. Whenever we've been in droughts, people are hoping for the El Nino. So do the patterns and the timing and the strength of the ENSO event. So this is talking about the ENSO events are right up here, and this is measuring the El Nino and the La Ninas. And it says, do those match the timing of a recent global temperature change? So I said no. Actually, that's a very bad thing to compare in the first place, because if you look at this is 1987. This is over the course of my lifetime, as you can see here. So this is only 33 years. Okay, so this 30-year graph, you can't really compare to things like this. This is comparing 800,000 years, or even back up, I think higher. There was the other graphs that were I can't remember this way. From I think the last lessons that talked some about climate that are going over thousands or hundreds of years, and this is only 30 years, so you can't kind of make those comparisons. Um, the other thing is that this text here tells us that there is a pattern of, looking for it, somewhere in here it talks about how the pattern is only 1 to 7 years for the El Nino and the La Nina. I can't find it in the moment. In somewhere in here it says this. And you can see that over the period of this time, right? This is 30 years, but it's going up and down and up and down and up and down and up and down. There's really not a common trend here, and especially when you're trying to compare it versus 800,000 years. So you can't really make that conclusion that those have to do with the global temperature change. Another thing that could change on Earth's surface that affects our climate is changes in the atmosphere. I was just talking about changes in the ocean, right, or changes on the land, which is like the glacier, but there's also changes in the atmosphere. So this talks about volcanic eruptions. Volcanic eruptions is talked about quite a bit because a lot of times people that don't believe that the scientists, when all the scientists say that climate change is a big human-made problem, they'll say like, well, volcanoes, look at all this stuff that volcanoes release into the air. But we've, studied, actually it goes down here. So we've studied volcanoes quite a bit, and we can measure how much carbon dioxide we release into the air, and we can measure how much volcanoes release into the air. So we are releasing 67 times more carbon dioxide than volcanoes do on average a year. So it's not a fair comparison. Also, fun fact, the types of carbon dioxide, right? So carbon dioxide is made out of molecules, right? And if you remember elements, there's like the protons and the neutrons in the middle, and then there's the electrons on the outside. And inside the nucleus, the number of protons determines the type of atom that it is. But there can actually be different numbers of neutrons, and those are called isotopes. You learn about that more later. But we can actually tell that the CO2 in the air that's increasing is actually a particular isotope that is only released when you burn fossil fuels. So the carbon dioxide that volcanoes erupt with is actually a little bit different. Anyway, so this says what factors might be contributing to the phenomenon at Shishmaref, which is that town from above. So I said, what you have happening is, way back at the beginning, what you have happening here is you had all this land that was frozen and it was ice. And so then, because it's getting warmer everywhere, for a lot of different reasons, this ice is melting, right? Maybe it's just hotter, maybe it's just not as cold, but the ice is melting. But as the ice melts, it is revealing more and more and more dark soil, and that soil washes away really quick to expose, new soil. Like imagine if this was flat, then all of this wall of soil wouldn't even be exposed to the air. But it is because the soil is washing away really fast, and as it washes away, it's dark. It absorbs even more energy, which makes it even hotter. So as it melts, it just keeps getting worse and worse and worse and worse and worse and worse. Moving along, moving along. All right, exploration 3. These show that the global temperature has increased on average. Some places are colder, but on average, definite increase. So these are all indicators of a warming world. So we have the humidity is increasing, the temperature over the oceans is increasing, the sea surface temperature is increasing, the ice in the sea is decreasing or melting, and the sea level is rising. So, as the ice melts, the sea will go up. And the glaciers are decreasing. So glaciers, which are usually just annual, it's like ice that's normally always frozen in mountains and in Antarctica and places. Those are getting smaller. So they're melting, but then they're not refreezing. So they're getting smaller every year. There's less snow overall throughout the whole world, right? This is averages for the whole world, and the land temperature is increasing. So, signs of the warming world. So now we have these graphs, and these graphs are talking about identifying correlation and causation. And this is an important thing to understand just because, so right here it talks about how this is showing ice cream sales, and this is temperature. And so you can see how as the temperature, as you can imagine, as it gets colder, right, you're probably not going to be eating as much ice cream. So these graphs show what we call correlation. And correlation means that as one of the thing increases or decreases, the other thing is increasing or decreasing. So these two things show correlation. These two graphs also show correlation, right? As the number of adoptions, I'm just kind of summarizing this, but as the number of animal adoptions is increasing, the temperature is also increasing. This is a correlation. Now, usually people mistake the words correlation for correlation with causation. So just because two graphs correlate doesn't actually mean that they have anything to do with one another, which a lot of times on people on TV or people that don't understand math very well will make this mistake. So they'll see these two graphs and they'll think that these have to do with each other. And these actually probably do have to do with each other, right? Because if it gets colder, you can imagine that people will buy less ice cream. So there's a really good argument that this is correlation with causation, like the ice cream sales decreases because the temperature is decreasing. But here, this is a good example of a graph that has correlation, but it is without causation. There's no cause for these two things to be related. So why would the temperature increase as the number of animals were being adopted? Or as it got warmer, why would more animals get adopted just because it's warmer? So these two things, right, they do have a correlation because they look similar, but they don't necessarily have causation, meaning they're not actually affecting one another. A perfect example of this is one time I was watching or I saw like a video or something on YouTube, and they were talking about GMOs, right? And so they were like, look, as people, and they had two graphs just like this, and they were like, look, as food products use more GMOs, right, the number of diseases also increased. But then if you literally found a graph for like the number of organic foods that were being purchased, that graph also looked the exact same. So it was like, well, you could just use, like, is it GMOs or is it organic foods that was making people have more disease? It's like, just because the graphs look the same didn't mean that they actually had to do with one another. So, and these two graphs are looking at that. So this is talking about, do these two graphs show correlation? And they do show correlation because they're both going up, right? They're kind of like going up at the same time. So these have correlation. But how could you figure out if they have a causal relationship? How can you tell if they're actually, how do you know if this one is going up because of this is happening? Like this is the temperature. So how do you know that the temperature is going up because of the CO2? Or how do you know that CO2 going up is related to the temperature? And so if you didn't know that, you would have to try and figure out if they're related. So the things that I said were, I might research CO2 if I didn't know what that was, because if you researched that, then you might find that CO2 can like capture energy, and that might make you help make a better conclusion. Or there's also you might want to see if maybe if you got another 100 years of data, or maybe this was from the Earth's atmosphere, but maybe you could just uh, take local things and see if you could find other examples of the temperature increasing as the CO2 decreased. Because if you had more examples that showed the same thing, then you could be more confident that these two things are actually related. I'm going to skip this one. So, causes of recent climate change. So, here we go, this thing. Most of the carbon dioxide that has entered the atmosphere in the last century is from burning fossil fuels for transportation and to generate electrical energy. So we burn fossil fuels for most of our energy. Every time you turn on a gas stove, that's a fossil fuel. Anytime you put gas in your car, fossil fuel. Anytime, usually when you're getting energy from electricity from your wall, that's coming from burning a fossil fuel. And we know that it's from the carbon dioxide specifically is from burning fossil fuels, because that thing I said before where there's like the different versions of CO2. You can have like carbon dioxide molecules with a certain number of neutrons, and then there's one with a different number of neutrons. And when you burn fossil fuels, it releases one of them. And so we know that it's CO2 from burning fossil fuels opposed to volcanoes or, like trees, making more CO2 or something like that. And said, how could the human decisions and behaviors contribute to the erosion in that town in Alaska? And, our actions basically affected the entire time for all of it, because everything that we're doing is warming. And so we are, and even building things close to the shore and on ice, or counting on these things being around forever, but they're not. So because we built them, then the erosion is happening more often. People driving around the area and walking around the area would make erosion happen even faster. So, burning fossil fuels and stuff, and then just living in the area would make it worse as well. And this is something I talked about already this is the positive feedback loop. I talked about that. It's when the land gets darker, there's more of it, so more of it gets warmer. Okay, lastly, the effects of climate change. So here we have this picture, woolly mammoths and saber-toothed tigers and bison. Not buffalo, bison. They're called bison. What would it look like now? So here, I drew it. This is a river. This is a river right here. Got some rocks. It's grassy. There's trees that are growing. Same trees, kind of. And there are mountains in the back. Maybe the mountains have snow on the top. Maybe they don't. But it's going to be warmer. Obviously, it's somewhat warm because you can see how there's grass here. So it's not like this doesn't look like a place that's frozen all the time. So it would probably be more just mid-range temperatures all the time. So effects of recent climate change. So changes in the biosphere. So a lot of animals have been affected by changes of climate change, because a lot of times they use the example of pika, right? Pika live in mountains, right? And so they're like these little like hamstery dudes, and there's no way I could draw this that big. So anyway, the pika, they live in a very particular range of mountains because they have to be a certain temperature, and so as climate change has taken place, right, they've had to move higher up the mountains, which gets them away from there's bushes and stuff that they hide in, so they're exposed more often. And then, because they're exposed more often, then when the winter storms run in, it tends to kill them because they had to go higher up the mountains to survive. So there's all sorts of problems with habitat that animals have to deal with, and that is causing them to die off because they can't adapt quickly enough. Here's more like the ice is melting, the permafrost is melting, the oceans are getting warmer, which is causing the corals to bleach and die off. because corals live off of a bacteria that lives on them, but then when the water gets too warm, bacteria can't survive, so then they don't have any food. So how could the increase in global temperatures over the last century be related to the events in this town in Alaska? And worldwide, the ice is melting, and that town is built on permafrost, and this is just ice, so it's melting. So as the Earth has warmed a lot over the past 100 years, a lot of that land has been lost because it keeps melting. And this talks about us and greenhouse gases, and something to recognize is that we can be affected by climate change. So what are two ways that we could be susceptible to climate change? And one is that we would be more susceptible to conditions like heat stroke or heat-related illnesses. Maybe people that have like paler skin tones, they're going to suffer more from like skin cancers and things like that, because during the summer months they're going to be more exposed to light on a regular basis and UV rays. Older people, children, and animals will have a harder time as it gets much warmer, especially during like the really hot months. And that could change how food is growing, and that can make things harder to find because maybe things used to grow locally, but now they don't. And then we need to think of ways that we can solve it. So some things that we can do is change behaviors that we know contribute a lot of CO2. So examples I wrote was such as buying fast fashion clothing. That's like the term for clothes that are really cheap, like at Forever 21, places like that, where it's really cheap, but most of those clothes are never bought, and they use a ton of resources that basically just get thrown away. Or using single-use items like straws, cups, plastic water bottles. Why buy a package of 100 plastic water bottles that you're going to throw away when you could just buy a single, reusable bottle? So things like that. And lastly, this is evaluating solutions for climate change. So in the problem is carbon dioxide in the atmosphere is causing temperatures to rise. And these are two solutions of how can the concentration of carbon dioxide in the atmosphere be reduced. So this is two ways to get there to be less carbon dioxide in the atmosphere. So solution one is remove the carbon dioxide from the atmosphere by planting trees in deforested areas. So if you plant trees in deforested areas, there's going to be more trees, and the trees are going to breathe in this CO2 and use the carbon in the CO2 to make the actual tree, right? Trees are made from carbon in the air, not from dirt. So that's one solution. The other solution is dump fertilizer into the ocean, and that will help the green algae in the ocean grow better, which is a kind of plant. And as that plant grows, it's going to remove carbon dioxide from the air because it's going to, it's breathing in that carbon dioxide, and it's using it to make itself from the carbon in it. And so that locks up that carbon dioxide into itself. So what are the strengths and weaknesses of both of these? So I said that planting the trees would be good because it would fix the deforested areas, but it's going to be really expensive to clean up a deforested area, because usually deforested areas are pretty bare and ruined once they are forested. So the companies that were going to do it, right, they would have to clean up a lot more before they could plant trees and have the trees actually grow. And it would also take a long time for the trees to grow. So fertilizer in the ocean would be really fast, and it would be a great way to get the carbon back into the oceans really quickly. And you could do it a lot, but it could definitely cause algae blooms, like we've talked about before, and that could damage the other life in the ocean, which kind of defeats a lot of the purpose. And you wouldn't necessarily know the long-term effects of dumping fertilizer into the ocean. You're basically dumping chemicals into the ocean too. So yeah, so there's drawbacks to both, but both could also be a solution. So that's just kind of evaluating what those are like. Anyway, if you have any more questions, come to office hours.